In this lecture, we will be addressing the issue of concavity. So, our definition of concavity will deal with a differentiable function. So, suppose f is a differentiable function at x equals a, and that L is the tangent line to the graph of y equals f of x at the point a f of a. Then we say the function f is concave upward or concave up at a if on some open interval containing a, the graph of f lies above L. F is concave downward or concave down at a if on some open interval containing a, the graph of f lies below L. So let's examine visually what happens in these two cases. And so in the first case, we have the function being concave up, and suppose we're here at the point a f of a, and we have the tangent line, which we'll call L. This definition says if you can find an interval, any open interval, containing a. So let's just think that we have some interval here that contains a. And over that interval, the graph of f lies above L. So the graph of f looks something like this. Then the function is concave upward or concave up at a. And it doesn't matter how wide this interval is. It could be really tiny, as long as there is one. For the second part of the definition, we just flip that picture upside down. So now we have the point a f of a, and again, we have our tangent line, L. And in this case, we're saying you have some interval containing a within which the graph of y equals f of x is always below L. This is what it means for the function to be concave downward at a. As long as you can find an interval of any width that contains a where this holds, then you can conclude that your function's graph is concave down at a f of a. Now, let's bring into the fold the case where f double prime exists. So now we assume that our function is twice differentiable on an open interval I. If f double prime of x is positive on I, then f is concave upward at each point in I. If f double prime of x is negative on I, then f is concave downward on each, or for every point in I. And this was this idea that we explored when we first looked at what the sign, S-I-G-N, of the second derivative meant. And the idea was, if you're at a point, say, x1, that's on the graph, and we're talking about case 1 here, where the second derivative is positive. Well, what that means is that if you have a tangent line as we move from left to right over the interval, the function f prime of x is an increasing function because its derivative, f double prime, is positive. If f prime of x is an increasing function, then as we move from left to right on I, f prime is getting larger. What is f prime? It's the slope of the tangent line to f. So as we move from left to right, say to x2, if we draw the tangent line, the slope of the tangent line has to be higher. And this has to hold as we move across the interval, and the result is that the function's graph is concave upward. And we have the analogous situation for 2. In 2, we're saying f double prime is negative, which means f prime is decreasing. So if we draw a tangent line at, say, x1, now as we move from left to right, the slopes of the tangent lines have to be decreasing. So the slope of the tangent line at this x2 will be less than the slope of the tangent line at x1, and the result is that your function has this concave down shape. So this is how the second derivative fits in to the story regarding concavity. One thing that's worth pointing out is that as we understand what the sign of the second derivative means, it tells us completely different information than we get from the sign of the first derivative. And the way we can see that is look at the 4 cases. F prime is either positive or negative. F double prime is either positive or negative. And let's leave, we're not including the case where F double prime or F prime is 0. So in the first case, if f prime is positive, that means the function is increasing. If f double prime is positive, it's concave up. So we have something like this. So we're increasing and concave up. Over here, we have the case where f prime is positive, so we're increasing, but f double prime is negative, so we're increasing and concave down. So the function is going up, but is concave down. Now we look at the cases where the derivative f prime is negative. So in both of these cases, the function is decreasing. So in this first case, f prime is negative, so the function is decreasing. F double prime is positive, so it's concave up. So we have something like this. And in this case, f prime is negative, so the function is decreasing. F double prime is negative, so the function is concave down. And this should illustrate that we are getting completely different information from both the first derivative and the second derivative. First derivative just tells us increasing, decreasing. Second derivative, concave up or concave down. Let's revisit an example. So we had looked at this example earlier in a previous lecture, and we had found that it had a local maximum at the point -1, 3, and a local minimum at the point 1, 1. 1 minus 1. But let's check the concavity. So we have f prime of x is 3x squared minus 3, and f double prime of x is 6x. So we see f double prime is positive if x is positive, and f double prime is negative if x is negative. And so this tells us the original function f is concave up where f double prime is positive. So it's concave up on 0, infinity, and concave down where x is negative, or minus infinity to 0. If we graph our function, so we had the point 1, minus 1. That was a local min. And then we had minus 1, 3, which was a local max. And we can check that the y-intercept of this is 1. And we see from our second derivative analysis here that the function is concave up on the positive x-axis and concave down on the negative x-axis. And so we can actually get a picture of the function, and we know it looks something like this. So again, we are concave up to the right of the origin and concave down to the left of the origin. But note, we switched from concave up to concave down when x was 0. That was the case where f double prime equals 0. So f double prime of 0 was 0, and the concavity switches at that point 0, 1. And we give a special name to that kind of point where the function actually changes concavity. We call that an inflection point. So the point A, where f is continuous, is an inflection point of f, provided that f is concave down on one side of x equal a, concave up on one side of x equal a, and concave down on the other. So the idea is the function changes its concavity at that point. And the way we test for it is, as was illustrated in the previous example, if you have f double prime existing on an interval containing a, then a is an inflection point provided that f double prime is negative on one side of a and positive on the other side of a in I. And so the idea, again, is that at x equals a, f is switching its concavity. How do we find inflection points? Well, either f double prime of a is 0 or it doesn't exist. These are the only two possibilities. And we can draw an illustration to show all the possible types of inflection points. So you can have an inflection point like this. At this inflection point, we have a vertical tangent line. And so at this point, f double prime does not exist. Yet we switched from concave down to concave up. The idea here is because f prime doesn't exist. And if f prime doesn't exist, right, f prime doesn't exist because we have a vertical tangent line. Well, if f prime doesn't exist, certainly f double prime cannot exist either. We can also have a cusp or a corner point. So this would be another type of inflection point, say x2. So a cusp or corner. And in that case, again, f double prime does not exist. We can also have something like we saw in the previous example, where you actually get this change in concavity. So this would be the case where the function is decreasing So f prime of x3 is negative, but we have a 0 in the second derivative. We can also have an inflection point where the function levels off. In this case, this would actually be a critical point of the function. So here we'd have f prime of x4 equals 0 and f double prime of x4 equals 0. And these would be the different types of inflection points that you would see. So again, cases where the second derivative doesn't exist, or cases where the second derivative is 0 and you have that concavity switching in this smooth way. We now take a look at an example, which is kind of the classical example from a differential calculus course, which brings together all of the information about f, its first and its second derivative, to graph the function. So we are asked, given this polynomial, to find and classify its critical points, which means determining any local extrema. Determine where f is increasing or decreasing. So that's first derivative information. Then we go to second derivative information. Find inflection points and then intervals of concavity. This is a type of question that you want to have down pat for things going forward like homeworks and exams. Okay, so we know the first thing we need is the derivative. So we want to get f prime is 12x cubed minus 12x squared minus 24x. And we know that we're going to have to find zeros of this and use the first derivative test to find where it's increasing or decreasing. So it's usually best to try and factor this if we can. Write it as a product. We see we can factor a 12x out, and that leaves us with x squared minus x minus 1 minus 2 which further simplifies because we can factor the expression in the parentheses. That'll be x minus 2 and x plus 1. So when we start in on the critical points, remember that means f prime equals 0 or f prime does not exist. This, of course, being a polynomial, there's no issue with f prime's existence, so it's only this first part. F prime of x equals 0 gives us, based on our factorization of the first derivative, 12x equals 0, x minus 2 equals 0, and x plus 1 equals 0. So this gives us the points x equals 0, x equals 2, and x equals minus 1. Those will be the x values of our critical points. Now, since we're graphing this, we should also find the corresponding y values. So first, f of 0, we see when we plug it into the original 0 into the original function, we get minus 1. So we have 0, minus 1. When we check f of 2, we plug in 2. So 3 times 2 to the 4th. 2 to the 4th is 16. Minus 4 times 3 cubed. Times 2 cubed, which is 8. Minus 12 times 2 squared minus 1, or 48 minus 32 minus 48 minus 1. Conveniently, the 48s cancel, and we get minus 33. So our second critical point is point 2 minus 33. And then for our last one, we plug in the value for x equals minus 1. And so we'll get 3 minus a minus 4. So 3 plus 4 minus 12 minus 1, or 7 minus 13, or negative 6. So we have found all of the critical points for this function. And remember, local extrema may happen at these points, may not as well. But if we have any local extrema for f, they have to occur at these points. We now move on to identify these critical points as local extrema or not. And remember that we can use the first derivative test for that. That always works. And sometimes we can use the second derivative test for that. We're focusing on the second derivative in this lecture. Let's use the second derivative test. So here we have the second derivative of the function. And we can plug the x values into this second derivative. So for instance, at this critical point, we see the second derivative is negative. What that means for this function is that at the point 0, negative 1, that's a critical point. So we know the tangent line is horizontal. We also know from the fact that the second derivative is negative at this point, that there's a small interval, there's an interval of some size around this point for which the function is concave down. That, via the second derivative test, allows us to classify that this point 0 minus 1 is a local maximum value. And we take similar steps for each of these other critical points. Plug the x value in. So for x equals 2, we get 36 times 4 minus 24 times 2 minus 24. (36 times 4 is 144 minus 48 minus 24, or 144 minus 72, which is 72. And again, all we care about is that this is positive, which means at this critical point, near this critical point, the function is concave up, which means the point 2 minus 33 is a local minimum for f. And then finally, plug in minus 1 to the second derivative, and we'll get 36 plus 24 minus 24, or 36, which again is positive, which means the function is concave up near the value of x equals minus 1, which means we have a local minimum at minus 1 minus 6. So we've identified the 3 local extreme values for this function. We still have more to do. We have to figure out where the function is increasing and decreasing and where it is concave up or concave down. So let's look at increasing and decreasing first. So we have here our derivative written as a product. We've broken it down into as many terms as possible. And remember, to do this, we set up our chart. And what we care about here is the sign of the first derivative. and we write all of these terms from the product that form the first derivative down here. And then we have to put our x values and list them in increasing order. And remember our critical points. We had x was equal to, if we look back in the previous slide, we had x equals -1, x equals 0, or x equals 2. So -1, 0, 2. And we list those in increasing order here. So -1, 0, and 2. And we check on either side the sign of each one of these terms. And remember, the way that we do that is you pick some representative value from the range of x. So down here, we need something that's smaller than -1. Say -2. 12 times -2 is -24, so that's negative. Something in between -1 and 0, say -0.5. 12 times -0.5 is -6, negative. Something in here between 0 and 2, how about 1? 12 times 1 is 12, that's positive. And then if we pick something bigger than 2, say 3, 12 times 3 is 36, positive. And so we go through and check this in each of these cases. So x minus 2, again, something smaller than -1, try -2. -2 minus 2 is -4. Something between -1 and 0, how about -0.5? -0.5 minus 2 is -5/2 or negative. Something between 0 and 2, how about 1? 1 minus 2 is -1, negative. Something above 2, say 3. 3 minus 2 is 1, which is positive. You can do this in a more holistic way if you want as well. You can check, say, you can look at a term like this one and say, okay, we want, when is x plus 1 negative? And you could say x plus 1 is negative if x is less than -1. And then you can use that to just fill the chart in and say, okay, this is negative here, and then it's positive at these other points. However you want to fill in this chart, you're picking representative values in between these different critical point values, x values, and just checking the signs of the terms whose product makes up f prime. And remember, we just multiply up. Minus times a minus times a minus is a minus. Plus times minus times minus is plus. Plus times minus times plus will be minus. And then plus times plus times plus is plus. And now we have the increasing, decreasing information, because remember the first derivative test tells us here we see f prime of x is negative in this interval and negative in this interval. So since we have that information, we know that to the left of -1, f is decreasing. So f is decreasing on -∞ -1, as well as this interval 0, 2. And then when we see that f prime is positive, we know the function is increasing. And so we see f is increasing between -1 and 0, and then to the right of 2. And so we have our increasing, decreasing information. Note that there's some redundancy. We actually could pick up where these local extrema are. The first derivative test would say here f prime is negative, so the function's decreasing and switches to increasing at this critical point. So the function would have a local minimum here at x equals -1. With 0, the function is increasing to the left and then decreasing to the right. So you'd have a local maximum value, and then at 2, the function is decreasing and then switches to increasing. So at 2, you'd have a local minimum. So you can also get your local extrema from this test as well. And this test will always work for that. So the last thing we were asked for there was concavity. And so we need to check the sign of the second derivative. Now, it's often the case with these problems that it's usually that either the first derivative information works out nicely and the second doesn't, or the second derivative information works out nicely and the first doesn't. When you see a problem like this where we had nice x values for our critical points, it's often the case that the values aren't so nice for the second derivative information. And we will see that is in fact the case here. And we want to check, the way we check for concavity is very similar to how we checked for a function being increasing and decreasing. It's just what we care about now is the sign of the second derivative. And of course, the sign of the second derivative changes value at critical points of the first derivative. So we need to solve f double prime of x equals 0. That's how we're going to find our inflection points. So here we have a factored version of our second derivative, and we need to solve 3x squared minus 2x minus 2 equals 0. And this requires the quadratic formula. So we have a, b, c, and we will get solutions x equals negative b plus or minus square root of b squared minus 4ac all over 2a. So the usual thing, usual quadratic formula, and work this out, and we will get solutions of x equals 1/3 plus root 7 over 3, and x equals 1/3 minus root 7 over 3. And by the way, those are, because we're going to graph this, the first is approximately 1.215, and the second is approximately negative 0.585. And what we do now, again, is very similar to our test for the first derivative. We want to check the sign of f double prime. And you want to write f double prime as a product if you can. Here we can't reduce this. So we'll just have the one column, or the one row. And again, draw your values, your critical points. These are critical points of f prime. So we have the smaller of the two first, 1/3 minus root 7 over 3, and then the larger one, 1/3 plus root 7 over 3. And again, this is just how it goes. These numbers often don't work out all that nicely in at least one of the cases. And this helps for us to realize this smaller one is about minus 0.59. And the bigger one is about 1.22. So like before, pick representative values in between these and plug them in to the second derivative. So plug in what's a nice value between minus 0.59 and 1.22. How about 0? F double prime of 0 is minus 24, which is negative. So the second derivative is negative in between these two values. How about something bigger than 1.22? Let's try f double prime of 2, which we've actually already checked. F double prime of 2 was 72, which was positive. So we saw that the second derivative was positive over here. And something smaller than minus 0.59, we could check f double prime of minus 1, which we already also checked, which was 36, which was positive. So we saw the second derivative was positive there. This means we have now figured out the concavity, so the function is concave up to the left of 1/3 minus root 7 over 3, concave down between these two 1/3 minus root 7 over 3 and 1/3 plus root 7 over 3, and concave up to the right of 1/3 plus root 7 over 3. So these 2 points are, in fact, inflection points of f. And we now summarize this. So these are points of inflection. Maybe we'll go through it first. Let's summarize everything. Local minimum values at these 2 points, local maximum value at this point. We determined where the function was increasing and decreasing. We've gotten these intervals of concavity. So to the left of 1/3 minus root 7 over 3, and to the right of 1/3 plus root 7 over 3, we were concave up, and we were concave down in between those 2 points. And to answer the question, we also should point out we have inflection points at x equals 1/3 minus root 7 over 3 and x equals 1/3 plus root 7 over 3. And now let's actually draw the function using all of this information. So we have to tinker a bit with our scale for this function, because we see our x range from -1 to 2, but our y range from -1 all the way down to -33. So we can say here's x equals -1, x equals 1, x equals 2. Let's get these points on the graph. So first we have our local minimum at the point 2, -33. So we have a local min there. Then we have a local max at 0, -1. And a local min at -1, -6. And by the way, drawing these really helps to actually fish out any mistakes you might have made. For instance, if we saw that if we had somehow misclassified this right-hand point as a local minimum, we would see that it's not going to make sense given that we had a local minimum here. How would we get down and get a local minimum without coming down and coming back up? Because this function is differentiable, it's a polynomial. So you can often pick up on mistakes you might have made when you do this. Okay. We also now have our inflection points. So our points of inflection, we'll draw in orange. One of them is at about -0.58 for x, which is a little bit over halfway to -1 from the origin. And then the other inflection point is at about 1.2. We are increasing on the interval -1, 0. So we're increasing here. So the function has to be going up, and we change concavity at this point. So let's see if we can draw that. We're increasing And then we change concavity. So we should have something like this. Now, going from -1 to 2, going from 0 to 2, the function is decreasing, so we're going to fall. And we change concavity at about 1.2. So the function will fall and then switch concavity there. So we should hopefully have done a decent job getting our inflection points. And then the function is increasing from 2 to infinity. And the one thing we missed here, the function is decreasing from negative infinity to -1. So as we come from the left, we're going down. So this is a graph that captures all of the information that we just used. And if you wanted to label it, you could get kind of a, so we would be increasing in these purple ranges. So -1 to 0, and then 2 to infinity. We could say that we're decreasing in these yellow labeled intervals. And to not muddle up the picture too much, the points of inflection kind of show us we're concave up to the left of this point of inflection and to the right of this point of inflection, and we're concave down in the middle. So this gives us a pretty clear picture of what our function looks like, and this is really a classical problem in calculus. Differential calculus. Now, one thing that we didn't do is handle what's happening with the limits as x takes off to plus infinity or minus infinity. And we'll focus on that in a future lecture. But for the time being, let's just mention it, that the limit as x goes to infinity of our function f of x, remember f of x was 3x to the fourth minus 4x cubed minus 12x squared minus 1. And the argument when we did limits of functions like this is that it's the leading term that drives the boat. And because as we increase x without bound, x to the fourth is blowing up to infinity, and this first term is staying positive, this limit is infinite. So the function is taking off to infinity as x goes to infinity. And similarly, the limit, if we go the other way, as x goes to minus infinity of f of x, will also be infinity because the leading term has x to the fourth power. So x being large and negative is being squared away. Right? You have this even power. So this term is still blowing up and staying positive. So as x goes to minus infinity, the function is blowing up. We'll dig into the details of that in a future lecture. But again, this is really a classical calculus, differential calculus problem. Graph your function, graph your polynomial, incorporating all the information from the 0th, the first, and the second derivative. So function values at key points, identification of local extrema, identification of intervals on which the function is increasing or where the function is decreasing, and then identification of concavity, intervals where the function is concave up or concave down. This is something you want to make sure to have down pat, because it really does bring together a lot of what we learn in a differential calculus course.